chemical synthesis.
Thank you so much. First, I would like to extend my thanks to Professor Vivek, who actually gave me opportunity to expose my research to the top intellectuals of India, and especially very bright students around here. So, as you know, from last few days we have been having very intellectual discussion on the need of new catalysts which can perform sustainable chemical synthesis. So I don't have to further motivate you like why such a research is important, why catalyst development is important. So let me right away dive into the work which I am doing right now. So we pay a lot of attention on controlling sophisticated, well-designed nanostructures by controlling their nanoscale features and synthesize nanoscale catalysts, sophisticated nanoscale catalysts. So the idea is, as a human, we have created like very nice codes, infrastructure, buildings, well-designed everything, but still, in terms of heterogeneous catalysts, we are still using catalysts which look like rocks. So can we solve that problem? Can we have more smart and beautiful catalysts which can be more useful for performing synthesis? For example, in this sandwich-like nanostructure, we can include ultra-thin atomic layer of atomic layout, and by these overlayers, we can provide some microenvironment which can help actually to activate substrate molecules to give desired products. In other example, we can also add some additive ligands which can adapt into some microenvironment around the substrate on the metal surface and give you selectively one product. You can switch the selectivity based on the choice of additive here. Another more open designs like hollow structures or porous structures, you can actually control molecular diffusions or maybe the mechanisms by which energy can be directly supplied to the active sites and control the reactions in this way. Another area which we are pursuing that we want to interface well-designed nanocatalysts with the live microorganisms or living cells so that we can take simultaneously advantage of biocatalysis and chemocatalysis. So with this motivation, so for today's discussion, I will be mainly talking about this part. This part is actually very advancing right now, but in the next opportunity, I will discuss it. So such kind of ambitious research is not possible without the support of proper ecosystem. So I am fortunate enough to work with a small team of very talented co-workers here. Funding comes from the people of Korea through NRF, and then infrastructure is supported by the postdoc camps. So plasmon-induced catalysis, little basics. Actually, I will not go into details so much. Professor Vivek is already contributing a lot in this field. So, as you know, certain metals like gold, silver, copper, if you make them, if you synthesize them in nanoscale size, they have very unique effect, which is called localized surface plasmonic resonance. Due to that, you can actually concentrate electromagnetic field, or in other words, light, very efficiently on the nanoparticle surface. And that gives opportunity to perform reactions on the nanoparticle surface by unique pathways. So in terms of mechanisms, although we don't work very extensively in figuring out how different effects are participating in these reactions, Professor Vivek has a lot of he has created a lot of knowledge along this side. So there could be participation of hot charge carriers, which can be produced within the time scale of femtosecond to picosecond, and then surface electric field, localized heat. So there is an intricate effect of these all factors. So interestingly, all these features can be controlled by controlling shape, size, aspect ratio, sharpness, and many intricate nanostructural features within the same nanoreactor. But unfortunately, this kind of capability is available only in certain metals like gold or silver, which have limited catalytic power. So we want to interface some catalytically active metal with the plasmonic core, and based on this interfacing chemistry, you can actually control that how the energy gets transferred to the active sites. So, as far as synthetic strategies are concerned towards plasmonic catalytic nanoreactors, we use silica templates of different sizes, shapes, and porosity, because now soldier chemistry is mature enough that you have perfection, that you can synthesize these templates in very high yields and with size and porosity homogeneity. And then we, using these templates, we try to control the nucleation and growth processes inside these silica templates or around it to make these kind of diverse nanostructures. Each nanostructure has their unique features in terms of controlling the reaction, because they, by this variation we have made choices of interfacing catalytic compartment with plasmonic compartment. So we can have like coatings, different catalytic metal coatings on plasmonic nanocrystal surface with atomically thickness precision. We can also compartmentalize plasmonic and catalytic compartments separately, which will protect catalytic nanocrystals nicely, and the light will be harnessed in the proximal plasmonic component and it will be transferred to the catalytic sites. Another design is bi-layer design, where we can co-locate plasmonic hotspots with catalytic sites. These catalysts are very active for the reactions, and even we can couple two modules like magnetic and plasmonic together within the single nanostructure and perform two kind of reactions or two steps of the reaction simultaneously, with it individually controlling both by magnetic field and plasmonic and light. So for today, actually I have chosen this work particularly to present here. So if you want to control the reaction on the plasmonic nanoparticle surface, you have to, because always catalysis happens at molecular scale, and nanoparticles are actually several, 10 to 100 nanometer in size. So how you can create a microenvironment? By microenvironment, what I mean is molecular scale confined spaces. So there are several ways. You can modify nanoparticles with certain ligands, which may have some function. But as you know, ligands are usually conformationally flexible, and they can orient themselves in unpredictable ways. So that may poison the catalyst sometimes. Other ways, you can encapsulate plasmonic nanocrystals inside thick shells, porous shells like MOFs, zeolites, etc. But they have molecularly like restricted size, so the diffusion may be the slower. The third way is you can actually make like rectal kind of structure, where you can locate plasmonic nanocrystal inside hollow and mesoporous cells. But here, as you can see, the plasmonic nanoparticle is clean surface and reaction will be happening there, so you don't have much control on the selectivity aspect. So what we thought, can we make a unique metal organic interface where we can lay out a molecularly defined, well-defined, very flat layer which has porosity, which we can actually estimate how much is the pore size. And by using this thin layer, we can actually exert very beneficial effects, confinement effects, like geometric or electronic effects. Geometric effect will come from the pore size or geometry, and electronic effect will come from the atoms which are included in this organic layer. So this is another kind of alternative way of modifying some ligands, static ligands. But due to organic nature, this layer will also be the flexible one. So it can fluctuate and it can avail this interlayer space as well as this kind of well-like space on the metal surface. So as far as synthesis is concerned, so synthesis we start from, for example, any plasmonic nanocrystal you can choose, which you can synthesize in homogeneous sizes, encapsulate them in hollow silica shell. So why hollow silica shell? That actually stops them from aggregating, and you can, without any ligand or surfactant, you can disperse them in the solution. Expose that solution with the light. So when you expose it, there will be activation on the surface, and you can take this diol, which will be in situ converted to this dialdehyde, and you throw in this triamine, which will condense with this base chemistry, and then that may create this kind of pore by simple covalent organic framework formation chemistry. So we got inspiration from COF chemistry and used it. But for COF synthesis, usually you cannot control the thickness or size of those materials very well. So here, due to this surface limited chemistry, we could control the thickness within 2-3 nanometers. So that facilitated us that this thin layer will not restrict the molecular entry. And the size is, like sub-nanometer, but 3 to 4 nanometer size, angstrom size, which can actually easily accommodate any small molecule. As you can see in TEM, this PCOL layer, covalent organic layer, is conformally modified on the nanocrystal surface. And in the second step, we treat with the catalytic metal. So that catalytic metal actually goes to the metal core, and the CUF layer comes on the top. So this we characterize by many methods like ELS mapping and all. We also use several methods to confirm that there is in fact the presence of CUF layer, very thin CUF layer with well-defined molecular scale porosity on the plasmonic nanoparticle surface. And the catalytic metals are below, between the plasmonic nanocrystal and the CUF layer. For testing the performance of the catalyst, we chose this alkyne hydrogenation. As you may be knowing that alkyne, if you hydrogenate alkyne, so the first step goes fine. Actually, this is challenging, but the second step is thermodynamically more favorable. So it's difficult to control actually the reaction at this stage. So we thought that this PCOL layer will actually help us in controlling the selectivity of this reaction. So as you can see, you can disperse your catalyst in simple vial. So we actually custom made this vial by putting one quad window on the top, so that you can shine light through a collimator. So you can expand the beam as much wide as you want and avail the light with the flux whichever you decide. So we monitor the reaction with the NMR, and here let me explain you. So pay attention on this yellow lines, which is actually the main catalyst data. So over the time, as you can see, this square is alkene, this product. So that maintains like 100% selectivity. So during this reaction, when we never see within the NMR detection limit, we never see the formation of alkene. But when we do the same reaction with commercial palladium carbon catalysts, you can immediately see within 20 minutes the over-hydrogenation starts happening and selectivity goes down. So other catalysts also, we have a comparison with several control catalysts and found that PCOL layer is very crucial for controlling this molecular adsorption-desorption behavior. So in terms of mechanistic proposal, when in the normal circumstances, if you shine light, the plasmonic excitation will take place, that will activate the reaction. Metal hydride will form from the borane here, and this alkyne will accept hydrogens, and finally you will get this completely hydrogenated product. But when you have CUF layer on the top, this alkene product dissolves from the catalyst surface before it undergoes to the complete hydrogenation. So then we wanted to know like what is the actually happening. So for that we did some in situ reaction monitoring experiment. So as you know, plasmonic nanocrystals are very good in enhancing Raman signals, and you can actually use them for very sensitive detections during the reaction. So when we have like overlayer here, the alkyne peaks is this one. So over the time course, we never see alkene peak. So which indicated that as soon as alkene is forming, that is going out of the catalyst surface. We never see that, because if it is on the surface, it will again over hydrogenate. So it will confirm that the lifetime of alkene on the catalyst surface is very, very low. So in the second case, we remove the COL and we see that alkene exists, which is responsible for its over hydrogenation. Now the third case, we intentionally actually bound the alkene on the catalyst surface and found that it gets over hydrogenation even in the presence of PCOL, because right now this substrate doesn't have facility to fly off from the catalyst surface. So that's how actually we propose that there could be mixture of electronic and geometric confinement effect of this PCOL layer, which decides the easy desorption of the intermediate alkene product, and the alkene never forms. So what now we are doing, we are actually extending this chemistry to the chiral nanoparticle surface. So chiral plasmonic nanoparticles have ability to be activated by the polarity of the light. You can decide, right-handed light or left-handed light, and based on that you can activate the surface. And what we have actually achieved to transfer this nanoscale chirality to the molecules, prochiral molecules, which has never been achieved confidently. The enantiomeric access is very, very low because molecular reactions happen at atomic scale, but at nanoscale, how the chiral information transfers without any other bias, that is very, very challenging. So this manuscript is under preparation, so I'm not revealing much data in this direction. So if you want to know more about my research, you can go into these articles which we published in the last 4-5 years. Ongoing direction is how we can automate the optimization part. Optimization of catalyst is very, very important. So here we want to automate this process. So right now, hardly we are able to do 4 to 6 reactions a day, but our target is to do at least 10,000 reactions a day. So we are setting up that kind of facility in the lab. We have already written funding for that, probably within 6 months. Hopefully it may be accepted. And then from this data, we will predict which catalyst should actually be synthesized to test. Then we will need human effort there, and just so that we can synthesize some benchmark best catalyst in this area. So, Professor, like organometallic chemists, like Professor Mehti, they are very lucky. They already have, benchmark catalysts, well-defined ligands, metal center. You can characterize them nicely. But unfortunately, heterogeneous catalysts, if you want to buy some benchmark catalyst, that will look like something else. So you can only get information: what metal, how much weight percent, nothing else. Random particles. So our dream is, can we synthesize some benchmark catalysts which can be bought from the companies to test their own catalysts? So that's all my presentation is all about. If you have any question, please go ahead. Yeah.
We are on time, and thank you for your nice presentation. We can have questions from the students first. Students, come on, yeah, where is?
Hello sir, it was nice talk sir. My question is from hydrogenation of alkyne to alkene one.
Yeah.
So normally there are two possibilities of cis and trans one. And in your case, we have seen that the cis isomer is formed. And basically the trans is stable as compared to cis. So any comment on this?
So in heterogeneous catalysis, actually the reaction undergoes through adsorption. So unlike homogeneous catalysis, you have facility to rotate the bond as the intermediate forms. But on 2D surface, so it always goes through cis addition pathway. That's a basic mechanism actually. It has been known for a long time. So there is nothing like we have no effort in getting this cis. So PCOL layer has no influence on that. Any naked surface, metal surface can do that. Yeah.
Any other question?
You make it like cell layer in the pop cell layer in the nanoparticle, and you told that you are not using that another monomer, rather you are using diol and converting to this under light. I understand that.
Yeah.
This happened in presence of superoxide something, yes.
Yeah.
So then, like how you are controlling the formations, like in this case like cell formations, you are doing at room temperature or you are doing at the high temperature?
So we always maintain the temperature below 20 degrees Celsius. So that's how we actually, when you shine the reaction with the light,
yes.
so there is possibility the temperature may actually increase. Okay, so we control it. So we have very low flux. So the reaction doesn't seem to be thermal in any way. So that whatever reactions are happening, those are influenced by the surface. So as soon as surface is occupied enough, the reaction is self-cools. Because you have like inert layer in between.
Yes.
Any other question? if you don't have, I have a very quick question. I mean, just 30 seconds I have. So how does the cough layer help to release the alkene and no overreaction thereafter?
So we think that cough layer has lot of nitrogens. So those nitrogens are actually electron donating in nature. So they make surface very rich. So the alkene is very rich, already as compared to alkyne. So it changes the adsorption energy. So of course maybe it may not be well coordinated at this
Some
stage.
sort of non-covalent interaction.
Maybe. Yeah, maybe. So right now we are not able to resolve the steric and electronic effects very well.
Okay, thanks once again to the speaker for his nice presentation. On behalf of the organizer, we have a small token of appreciation.